So in this video, we're asked to use Taylor's inequality, which says if the absolute value of the n plus first derivative can be bounded by m for some x minus a less than or equal to d, then the actual error, will be bounded by this piece here, m over n plus 1 factorial times x minus a to the n plus 1. So we're going to find a bound in approximating natural log of 1.5 with a third degree Taylor polynomial for the function f of x equals ln of 1 plus x centered about 0. And then we'll compare that with the actual error. So let's start with what we need. First off, we need a third degree Taylor polynomial for this function, which means we're going to need the first three derivatives evaluated at 0. Now, f of 0 just equals 0, if you plug that in. Now let's find our derivatives. F prime of x is 1 over 1 plus x, but I'm going to write it this way. 1 plus x to the minus 1. F prime of 0 equals 1. F double prime of x equals negative 1 plus x to the minus 2. F double prime of 0 equals negative 1. F triple prime of x equals 2 times 1 plus x to the negative 3. So f triple prime of 0 equals 2. And we won't need this for our polynomial, but we will need the fourth derivative because we're going to need it for here. So let's just find it now. Negative 6 times 1 plus x to the negative 4th. Now we don't need to evaluate it because it's not going to be part of our Taylor polynomial. So let's find our third degree Taylor. That's going to be our first step in this problem. We have no constant term. The coefficient on x is just going to be 1, so it's x minus x squared over 2 plus 2x cubed over 3 factorial. Now this we can reduce. We can factor a 2 out of there with that one. And we get x minus x squared over 2 plus x cubed over 3. And you can probably imagine what the rest of the terms would look like. There's a nice pattern for this one. Now, what are we asked to do next? We're asked to approximate ln of 1.5. So in other words, we're asked to approximate f of 0.5 because if we plug 0.5 in, adding the 1 would make ln of 1.5. Is being approximated with our third degree Taylor polynomial, which would be a matter of plugging 0.5 in for your x's there, which comes out to be 5/12. So there's our approximation. Now, we're going to use Taylor's inequality to find the bound in the error. So let's talk about how we do that. First thing we have to do is we have to bound our Taylor polynomial on some interval. So let's see what our values are for these. So, well, we know our n plus first derivative. Now what we need to do is optimize this on this interval. Okay, so that's going to be the absolute value of x minus 0, since we're centered at 0, has to be less than or equal to d. Well, we're going out to 0.5. So that means we're optimizing this thing in between negative 0.5 and 0.5. So we need to figure out where the fourth derivative is going to be a maximum in between negative 0.5 and 0.5, which means we also want to check for critical values. So that would be checking the fifth derivative, which we can see would be 24 times 1 plus x to the negative 5. The only place it's going to be 0 is at negative 1, which is not inside our interval. So what we're going to do is check our fourth derivative at 0.5 and at negative 0.5. And if we do this, what we're going to get is at 0.5 we get And remember, we're doing absolute value. At 0.5, we get, at negative 0.5, we get 96. At 1.5, we get approximately 4.74. This is clearly larger. This is what we're going to use for our m. So that m that we were talking about as the bound is going to be 96. So now we can get our error bound. Our error bound in our third degree Taylor polynomial is going to be less than or equal to 96, so plugging that in for m, over n plus 1 factorial, which is 4 factorial because we have n equals 3, times, now remember we're doing this at 0.5, so 0.5 minus 0 to the 4th degree power. And if we calculate this, we get 1/4. So this is our error approximation. That's our maximum bound on our error. So our actual error should be less than this. So now we're going to find our actual error in our third degree Taylor polynomial, which is the actual value. We'll do the absolute value of 1.5 minus our approximate value. And according to this, we're hoping that it comes out to be less than 1/4. So if we calculate, we'll bring in our calculator here, we have ln of 1.5 minus 5/12. Again, we're looking at the absolute value. We see that we get an error of 0.0122, which is clearly less than 0.25. So our actual error in our third degree is approximately 0.0112, which is clearly less than our error bound of 1/4.